Sedimentation potential is a lot like streaming potential, except that instead of the liquid moving past the capillary walls, we have colloidal particles moving under the influence of gravity. So imagine we have a tube with an electrolyte solution in it and some colloidal particles. And we could imagine these particles being more dense than the electrolyte solution, in which case they're going to sediment. Or if they're less dense, they're going to rise to the top, they're going to cream. But in any case, they're going to move. So let's imagine these things have a positive surface potential. And we know that they're going to be surrounded by some counterions that are of opposite charge. Great. Well, as these things are moving, let's imagine that they're denser than the solution, so they're going to settle. The drag, the viscous drag on the particles and the viscous drag on the Gui-Chapman cloud of counterions is not the same. Since the cloud of counterions is going to be larger in radius, it's going to have a larger radius, it's going to lag behind. And so I'm going to draw this as sort of these teardrop shapes like this. And notice what we've done. We can sort of replace this solution conceptually with a bunch of dipoles. And we can see that for each sedimenting particle, we're going to have, for each particle that's moving, we're going to have, essentially we've created a dipole with negative on one end and positive on the other. So there's going to be now a potential difference between the top and bottom of the solution. So if we were to put a voltmeter here, we would see there would be a measurable deflection of the needle, showing that there's a potential difference between the top and bottom of the solution. Another way to think about this conceptually is that we've produced a bunch of dipoles in the solution, and that each of these is going to create an electric field. And if we add up all the electric fields of all the different dipoles of the particles, we can see that we now have an E field that looks like that. And since the E field has units of volts per meter, if we just take the strength of the E field and multiply by the length of the tube, we'd actually get a voltage. Okay, so the potential difference for sedimentation potential is the length of the system. So in other words, how far apart are these electrodes in terms of height? Dielectrics, the density difference between the solvent and the colloidal particles, gravitational constant G, and the zeta potential divided by the viscosity times the electrical conductivity. And let's annotate this just a bit. This is a positive number. We end up with an E field pointing in the positive direction. On the other hand, if these densities were flipped, the particles would cream. They'd rise to the surface, and we'd see the opposite sign for the E field. If we have a stronger gravitational field, we would get a bigger potential because we get faster sedimentation. And of course, we could induce this with a centrifuge or something. Also, it's proportional to the size of the zeta potential. That's obvious. If we have a more viscous solution, then things will sediment more slowly, giving us a smaller effect. And if we have a higher conductivity, the effect is also smaller. And that makes sense too, because we can imagine kind of it's basically, if we had infinite conductivity from top to bottom, we'd sort of short circuit this loop.